Okay, let's dive right into this explainer, the invisible architecture of urban airflow. Today we're zeroing in on a very specific focus, which is exactly how city buildings trap pollution right where we live and breathe. It's a seriously fascinating look at the unseen forces that dictate our urban environments.
So just picture this for a second. You're standing on a super busy city street. Cars are literally everywhere, and you can vividly smell that heavy exhaust hanging in the air around you, right? It's an everyday urban experience we've all had at some point.
But it brings up this beautifully simple yet kind of complex question. If the wind is blowing all day through that city, why doesn't the pollution simply disappear? Like, why does that exhaust smell just sit there? Well, the answer is actually a lot more interesting than you might think. See, we usually imagine pollution floating away in a nice straight line, right? Kind of like smoke drifting off a campfire. But the reality is completely different. Because buildings constantly disturb the wind, the air doesn't just move straight. Instead, it twists, it rotates, and it creates these massive invisible vortices. And it's exactly these flow structures that trap pollutants right down close to the ground.
Section Fluid Dynamics and Obstacles. Let's look at exactly how this works.
To really understand this invisible air problem, let's pivot for a second to a fluid we can actually see: water. So what do you think happens when exactly 1 kilogram of microplastics enters a flowing river? You'd probably assume it just gets easily washed away by the current, right?
Well, when engineers run a Python simulation of this, the results are pretty startling. Step 1, they create a simplified river flow. Step 2, they release thousands of particles. And step 3, they find that instead of washing away, many of these particles actually get trapped in the slow-moving regions directly behind the physical obstacles in the water.
As the researchers note, even after the water flows away, many microplastics remain trapped in the environment. Fluids, whether we're talking about water or air, they react to obstacles by leaving pollutants trapped in these dead zones right behind them, even while the main powerful current keeps on moving.
Section Inside the Street Canyon.
Now, let's apply that exact same river logic back to the city grid, where buildings are essentially massive obstacles in our invisible river of air. Engineers actually call this a street canyon. It's a situation where tall buildings act literally like canyon walls. They prevent the free-flowing wind above the rooftops from easily entering the street below. So the fresh air effectively gets blocked from reaching the street level, which is exactly where we're breathing.
Because of this canyon effect, we end up with this highly counterintuitive reality. Stronger wind doesn't always mean cleaner air. Sounds crazy, right? But when wind hits a tall building, the air separates. Some flows over the roof, some goes around the sides, and some is forcefully pushed straight down into the street itself.
And that downward force creates what we call a recirculation zone. It's basically a massive, rotating motion of air inside a street canyon that keeps car exhaust and pollutants trapped, bouncing between the buildings. It just circles around and around. It's acting exactly like those microplastics getting stuck behind the rocks in our river simulation earlier.
The real-world impact of this is huge. 2 streets only a few hundred meters apart can have completely different air quality. Just because of these localized vortex traps created by specific building layouts, the air you breathe can drastically change just by walking 1 block over. One street might have a clear, cleansing flow, while the very next block is a deep street canyon, trapping all the local exhaust.
Section Predicting the Invisible Flows. So, how do we fix this?
How do engineers predict these invisible traps before a city block is even built? Well, instead of just guessing, they use Computational Fluid Dynamics, or CFD. This tech mathematically solves the complex equations governing airflow. So long before a physical building goes up, CFD solves for wind velocity, pressure, turbulence, and crucially, exactly how pollutant dispersion will behave around the structures.
The big takeaway here is that the air around you isn't moving randomly at all. It's following the strict, predictable laws of fluid mechanics. And understanding these invisible flows through modeling is exactly how engineers can proactively design healthier cities, basically engineering out those dangerous recirculation zones altogether.
So, the next time you walk through a city, remember that invisible architecture swirling right above your head. And to wrap up this explainer, I'll leave you with a provocative question about urban obstacles to chew on. If buildings act as obstacles that trap dirty air, can trees actually make air pollution worse? It's a wild layer to this fluid puzzle, and we'll leave it right there for today.